It's my pleasure now to introduce our next speaker. It's Dr. Klaus Lackner. Klaus is trained in theoretical physics. He's worked on many things. He came to the United States and came to Los Alamos National Laboratory, which, as many of you know, is one of the major research centers for the Department of Energy in theoretical physics, in nuclear physics, and it's actually a place where the first atomic bomb was created. Klaus was very interested in many things and was recruited later in his career to Columbia University by Wally Broecker and Michael Crow, and became very interested in carbon capture from the atmosphere, from the air, which is a very, very hard problem. And in recent years, he has moved with the same Michael Crow, who's now the president of Arizona State University, to Arizona State University, where he has now been working on carbon capture from the air. So please welcome Klaus.
Thank you. Thank you very much for having me. I'm trying to talk a little bit about air capture, but I also like to put it into the bigger perspective of how do we actually manage carbon and balance the carbon budget. And I think if you listen to the discussion, and I got into this in the early 90s, we are not going about it quite the way we should. We are talking about mitigating, and we are trying to figure out how to raise efficiency, as you just heard a second ago, and find substitutes. But in the meantime, we are dumping carbon dioxide into the atmosphere, and it literally piles up like garbage. What convinced me very early on that I wanted to be in this, and it's Keeling's curve in the end, was the realization the stuff stays in the atmosphere and the ocean for a very, very long time. It may redistribute itself between the ocean and the atmosphere, but roughly speaking, half of that CO2 is with us in the atmosphere for hundreds of years, and getting out of the system of the mobile carbon pools, the biosphere, the atmosphere, and the ocean will take tens of thousands of years. So it's effectively permanent. And so we really should change, in my view, to a waste management paradigm where it's very good to reduce and reuse and recycle if you figure out how to do this. But if you can't do it, you can't just say, now I'm allowed to dump it into the atmosphere. You have to find a responsible way of disposing of that carbon dioxide. And in my view, that cost of that disposal, once it's generally accepted, is actually the natural price of carbon. And we then turn around and say, given that cost of disposal, it makes perfect sense to reuse it and be more efficient in using it. And in the end, you have to convince a lot of people and corporations and governments in the end to clean up this CO2 to garbage. And given the current politics, but also an observation that since Rio, which is now, 25 years ago, we haven't really succeeded with top-down approaches. Maybe we have to figure out a bottom-up movement like we had in recycling, where individuals, in the end of the day, decided that it's worth doing this, and then demanded structures which managed to make this work. So the carbon math, to me, is simply daunting. And I'm a little more extreme in my numbers than Sally. I noticed I put slightly bigger numbers up. But roughly speaking, 1 ppm in the atmosphere is 7.5 gigatons of CO2 in the air, right? And it spreads between the ocean and the biosphere, so it reduces it a little. And if you look at it on a 100-year time scale, I would argue 1 ppm is equivalent to 15 gigatons of CO2 emissions. So roughly, you put twice as much out as sticks to the atmosphere. And this is also what we are seeing. If you look at it right now, we are putting 36 gigatons or maybe 40 gigatons a year out, and the CO2 in the atmosphere rises by 2.5 ppm per year. And the current level of CO2 in the air is around 405 parts per million. I'm taking out these fluctuations, but I would also point out it's just about 450 ppm equivalent if you count the other excess greenhouse gases. And if you listen to the IPCC, they actually state it's the ppm equivalent which matters. So I would argue we may already have been run over by this problem, and we're already there, but we will find out over time because it takes time for things to settle. So I now said, well, if you know all of that, and we have 45 ppm left to go, you can ask how much have to be put on the brakes every year to actually stop at a certain limit. And you see, if you want to stop at 450 ppm, your carbon intensity, which is the carbon per unit of GDP, allowing for a 3% growth, is actually 8.4% per year. And I had a graph like this a year ago, and it really shocked me. I made a new one, and it went from 7.2% to 8.4% because we are still ramping up. And of course, the budget gets smaller every year, and the time gets shorter. So the annual reduction required is going up very, very rapidly. The other point I would make is if you think 700 ppm is an acceptable number, which probably nobody in this room does, it's still a 4%, a nearly 4% annual reduction in CO2 carbon intensity if we wanted to stop there. So if you told me that 700 is your target, I tell you, pull up your sleeves and get going, because even that is a hard problem. And of course, buried in there is the observation that we have economic growth, which sort of puts a 3% pressure on it. So having said all of this, another way of looking at it, rather than the garbage analogy, is to say we have a finite carbon budget and we are running into overdraft. We may already be in overdraft. If you think of 350.org, well, we are in overdraft. And the Paris Agreement holds warming below 1.5 or 2 degrees C. Well, then we are close to overdraft, and we cannot stop it anymore in time. By the way, if you look at where we would be with 450 parts per million, everybody on the planet gets one of those trucks. Here in the US, we go through them in about 5 years, so on a per capita level. So that is the scale. We are hitting limits soon, and so if we overshoot, we will need negative emissions, which means we have to figure out how to store carbon somewhere. And of course, all of this is coming up, represents an enormous business risk to people who are involved in all of this, and I think it's time for them to wake up and deal with that, because if not, they will get run over by the realities. And also, of course, creates opportunities for leaders who want to do something. So the IPCC now calls for negative emissions, and that means to me we have to recover the CO2 back from the environment. We either grow trees and collect them, that's one form of air capture, or we have chemical means of doing it. But that also means we need storage capacity. And if we come back by 100 ppm, which sort of to me is sort of a rough number we might be talking about, we are talking about 1,500 gigatons of CO2. By comparison, Lake Michigan is 5,000 gigatons of water. So we are talking on rather serious scales. And by the way, it's more than we emitted in the 20th century. So this itself is not small. And if we have to figure out a pathway back, well, this is easily 100 ppm we will have to deal with, because we may come from 500 to 400, or from 450 to 350, or if we are unlucky, from 550 to 350, which is 200 ppm. So can we build a carbon management industry in 30 years? Well, we have started with decarbonization. I think that makes progress. It's important. We need to do that. But I don't think it's enough, and it's not fast enough, and it's not large enough, because we have to go negative, and mitigation can't quite get us there. Adaptation is something we will have to do, because the train has left the station. We need to do capture and use. We need to capture at the point sources. We need to capture from the distributed sources. And it's great to have a market approach. You make gasoline, you have uses for CO2. But at the end of the day, certainly if we have to come back down, we will have to combine it with storage. And that, I think, gets you into the waste disposal paradigm. And I think before 2050, we are trying to balance a budget where we are taking away things which are going out. After 2050, we very well have to be coming down on a downward slope in order to get back to where we have to be, because I don't see us realistically stopping in time. We will overrun that 2-degree warming, and we have to figure out how to come back. So the big technologies you will need are carbon storage, and you heard a lot about this before, fuel synthesis, because that way You can close the carbon cycle without actually having to dig up more carbon, and that would, in the end, convert, in my view, renewable energy into liquid fuels. And it is ultimately based on proven technologies. It's sort of in the bucket of we can do that if we want to, but we are not quite ready because nobody asked us, and I think the same is true for carbon storage. Whereas direct air capture is a novel technology. I am working on it, a few other people are, and I think it still needs demonstration and scaling. So it's hard to make this work, and you see a few pictures of things we do actually to collect things, and I talk a little bit about it more in a second. But the technology gap there for me is direct air capture, and I don't think we can solve the problem directly with biology because we cannot grow enough to get to that 40 gigatons a year scale. And so the question then is, how do we close the carbon cycle via direct air capture? I think it's the only thing which can scale. The feasibility, well, we can clearly do it because we remove CO2 in submarines and spacecraft, and by the way, every air liquefaction plant before it actually makes liquid air removes the CO2 to make this happen. But we need to get the cost out because right now it's still too expensive. The good news in my view is that the cost imposed by physics, like thermodynamics, how much energy you need, is actually surprisingly small. So that is not what's going to get you. And other technologies have actually demonstrated that you can deal with even higher dilution. For example, people have shown that you can economically extract uranium from seawater. It's not quite economic in the sense that right now uranium is cheaper from other sources, but it's within a factor 2 or 3 of it. And there you are talking about 3 parts per billion, not 400 parts per million. And so we need to make design choices to make this work. And my view is you want to be passive, like a windmill. You want to use some energy efficient way. We are using a moisture swing. And ultimately, you want to go to mass manufacturing. So I view air capture as an enabling technology for several things. One of the things which is important is it eliminates all exceptions. Right now, if you go to Europe, power plants have to account for their CO2. Cars really don't because nobody knows how to get it back, right? No emission source remains exempt, which of course doesn't say you should do everything with air capture. You only use air capture where you have no other option. It also separates the sources from the sinks, which is actually quite important, and it may help on the power side. I have heard here in discussions coal plant utilities basically saying, look, we understand the problem, we are willing to do something, but it's going to be very expensive and it will take us a long time. If air capture exists as a competitor, you suddenly can motivate them to do it faster because let's face it, with 10, 13% CO2 in the flue gas, they have a lot easier time than I have to get it back from the air. As I just emphasized up to this point is air capture can draw down CO2. So therefore we could live in a world where we put it back and put it somewhere, but then we need vast CO2 storage capacity, and Sally just told you that we actually do have that. So if we want to, we can make that work. I think it also enables non-fossil liquid fuels because you can make synthetic fuels from CO2 and water, and you can think of this either as an energy storage play. If you have lots of wind and lots of solar energy, you have to balance, for example, over seasonal time, and it becomes energy storage in that sense. But also, I would argue an airplane, a ship, and a truck certainly have a much easier time driving on liquid fuels than operating on electricity or hydrogen. And by the same token, I would argue, even if all passenger cars go all electric, there's a really nice temptation to run a methanol fuel cell rather than having a huge storage tank or storage in batteries and actually lower the weight of the car and get yourself a 1,000-mile range and do that in the end. But of course, it requires that you can close the carbon cycle. The other thing I have to admit, and this is where I think I have political trouble, is it of course also enables fossil liquid fuels combined with carbon storage. And I do think that is actually a plus because we need to figure out how to make the transition without making too many enemies. And therefore it's nice to have an ability to do that. On the other hand, People who are very strongly into renewable tend to focus on that point and say, we rather not do this. On the other, it is what it is. So to me, I think of these things as mechanical trees. They stand passively in the wind. For our designs, I can tell you we are about 1,000 times faster in collecting CO2 than a natural tree. We can collect, of course, current and past emissions. We deliver CO2 for fuel synthesis or disposal, and we can operate at a global scale, and I will make that point a little clearer in a minute. And I would like to also point out air transport CO2 for free. So you can do it now in remote locations, and you don't have to do it right next to a major city, and you avoid large pipeline systems to move the CO2 where you want to have it. So it has downsides in the cost because it's so dilute, but it also has advantages. So it really comes down to, is it feasible and is it affordable? And I think there are sort of three things mitigating against it. The first one is known as Sherwood's rule, which says that costs typically scale linearly in dilution. And if you tell me that it's $10 to $100 to collect CO2 at a power plant, and I multiply that with 300 because that's the concentration ratio, I'm dead in the water, right? I need to come out, I would argue, below $100 a ton at the end of the day to be interesting. And if Sherwood's rule applies, we are in big trouble. The second part is it is very dilute in the atmosphere, but there's also a lot of water in the atmosphere, actually 10 to 100 times more, and we cannot become a water collecting device because $30 per ton of CO2 would be a very nice price for CO2. It's a horrible price for a cubic meter of water, right? So we cannot degenerate into a water collector. If we do, our costs just go sky high. And let's face it, a first-of-a-kind apparatus would be very expensive, and the APS in 2011, I believe, said $600 a ton is a number you would end up with. But that, I would argue, was a first-of-a-kind technology, which is also very, very energy intensive, and we have to figure out how to get cheaper than that. The lesson I learned from that is that it's not a conventional separation technology, but we need to think something better. So how do we avoid Sherwood's rule that the costs are linear in the dilution D? And if you look at Sherwood's original discussions, what he focused on was metals and pharmaceuticals. And in the metals, you see that he basically translates, the linearity translates in that the cost of a metal is constant in terms of the amount of ore, in terms of a ton of ore. And it turns out it's $10 per ton of ore in 1987 dollars. So if you ask yourself, what can you actually do for $10 a ton? It's not all that much. You can dig up a ton of rock, you can crush and grind it, you can run one flotation, and you can dispose of the tailings, which basically tells you the front cost dominates everything else. And if that is true, then of course you're linear. If you tell me I need to crush twice as much rock, it's going to cost me twice as much. So that A times D term is the bulk processing up front. And then, of course, thermodynamics says I need to pay a logarithmic term. That I can afford, but I can't afford that first term. So that multiplier A better be very, very small for us to make it work. And therefore, we aim to be passive. So what I show you here is our air capture aspiration. I put it here at $20 per ton because we are talking in 1987 dollars. And you know I'm way below this curve. And the same is true for uranium. And the way they got there is they are passively standing in the ocean current, and they are not paying for pumping and pumping water through filters. So we need to be passive too in order to get below that curve. And you can get that far below the curve if you are not tied up in the cost of the processing. So we want to be passive. Here's a little picture on the left of a small device which we actually tested in a wind tunnel. And so we want to be like a windmill, and it turns out the windmill harvests kinetic energy out of the air, which is 20 joules per cubic meter, whereas the CO2 content in a cubic meter of air would be resulting from burning 10,000 joules of gasoline. So in a way, the CO2 is 500 times as concentrated in the air than wind energy, yet we know we can make wind energy work. So standing passively in the air, and we have proven this in more detail, and I don't have time to do this right now, that it actually is only a few dollars per ton of CO2. The dominant cost for us is the second part, which is driven by the thermodynamics. We will have to pay more energy than the flue gas scrubber because we come from air where the dilution is lower. But we only talk about 20 joules we're only talking about 22 joules per mole of CO2. And if you look at where power plants would range, well, they are a little better, but not orders of magnitude better. So we conclude that we will have our costs in the regenerator. We will be more expensive than an optimal flue gas scrubber, but we will not be orders of magnitude more expensive, and therefore we can aim into the $100 range and even below that as we get there. Currently, there are a few companies who are doing it. There are a number of universities studying direct air capture. So I think it's becoming real, and it's worth pushing further. And our designs, we had this little device you see here standing on the roof for 9 months to actually figure out that we can collect CO2. This was, of course, catch and release. We measured how much we took, and then we sent it right back out, and the thing lasted for about 9 months. We are working on a monolith filter where we basically have the idea we stand in the wind. It just is good enough to let the air through and can absorb a good fraction of the CO2 that comes through. And so we are trying to aggregate this into sail-like structures. You see a wooden dummy here where we're trying to make this work. Hopefully in the next few months I can show you a picture of an actually working device. And so the idea is we can collect CO2. We collect it on a sorbent, which is an anionic exchange resin, which has the remarkable feature that these quaternary ammonium-based resins, when they are in the carbonate form and they are dry, I don't know what just happened, when they are dry, they have an extremely high affinity to CO2. It turns out that carbonate actually hydrolyzes with some of the remaining waters in the hydration shells into bicarbonate and hydroxide. The hydroxide absorbs the CO2, and if you make it wet, ordinary carbonate bicarbonate chemistry prevails, and the system actually 500-fold higher pressure in CO2 over it. You see this here, where I have the saturation and the equilibrium partial pressure over it for 20% relative humidity and 100% relative humidity, and you see a 500-fold increase in partial pressure. So that's the basic underlying concept. How would we move to scale? This is sort of an artist concept, how a 1 ton a day device would look like. Figure it fits into a shipping container, and it opens about 60 square meters of surface area to the wind in order to have access to the CO2 it needs. If you wanted to deal with 36 gigatons a year, you would need 100 million such units, and you can ask the question whether that's a large number or not. If you mass produce like this, they would likely get cheap because it's a manufacturing process. You would need to find markets in the beginning, and ultimately you want to get to this very large scale. If they last 10 years, you would have to build 10 million a year. And I want to point out that's a big number, but it's not an outrageously big number because Shanghai Harbor sends out 30 million full shipping containers a year, which says there's a production capacity 3 times larger behind Shanghai than we would need to do this on a world scale. And the world also builds 80 million cars per year. Now you could argue we are not building cars, but I think we are comparable in complexity, and ultimately our cost target is not all that different. So again, this shows that on a world scale, this is actually manageable. I would argue the low cost ultimately comes from experience. So here you see the APS at $600. I was involved with a startup many years ago, which estimated that its first of a kind would be $250 per ton of CO2. I think practical interest starts at $100, and I think all the companies who are in this space are sort of arguing they are close to that. I would argue that makes sense, but I can't prove it. And ultimately, the raw materials for ours, I can add up and capitalize, and I find out we are talking about energy and raw materials somewhere between $10 and $20 per ton of CO2 is unavoidable. Double that, so you're in the $30 per ton of CO2 range as a long-term target if the power of the learning curve comes into play. Whether or not that will remains to be seen. So there are now multiple value propositions in all of this, and I think I'll close on that. The first one is, I think you need to convince people to do this voluntarily, and this to me is a little bit how recycling turned into a business and how renewable energy is paid for today. People pay extra, a penny or two per kilowatt hour, in order to say their energy is sustainable and clean and green. And so we need to convince people that you should do the same here too. And I think volunteers then create a carbon price, and then regulatory policies can follow. I would never kid myself that volunteers can solve the problem, but they can give you the political background to make it happen. So imagine a button on the pump. And if the oil companies were to share at $110 a ton of CO2, half into the price, the consumer would have to pay 50 cents extra on a gallon of gasoline to make this happen. And ask yourself, would some of you be willing to push that button at a pump, or when you buy things overnight at Amazon and pay 50 cents extra to account for the gallon of gas which has been used to get you that parcel overnight? I think ultimately the value proposition to oil companies, to other players, is the societal license to operate in the environment, because eventually they will lose it otherwise, because without it, the carbon problem, the physics of the problem is such that we will have to stop. It therefore also protects the assets in the ground, and that I think is something oil companies should think about, but it also creates brand new business opportunities in carbon recycling and also in carbon waste management. And I would want to point out that waste management companies, not in the carbon realm, but in other realms, are very lucrative businesses, right? And I lastly would point out there are liabilities, and I would argue, notwithstanding the current EPA director, somebody in 2050 or 2040 cannot really claim ignorance in 2017 on climate change, and this will cause liabilities. And I think those are the issues which I think might help us to move forward. And I'm looking for a bottom-up as well as a top-down approach to make things happen. And I think air capture could democratize things, because it allows you to go after emissions you and I are responsible. Every time I step on the gas pedal of my car, I put CO2 out. Every time I take a hot shower, I am putting CO2 out and nobody else. And starting to go after that might be a good starting point. And I thank you for your attention.
Thank you, Klaus. We have time for some questions. John? Oh.
You touched on the infrastructure costs a bit with the 10 million units versus the 80 million cars, but those cars and those shipping containers are being manufactured by a certain resource and a certain infrastructure for a certain purpose. Wouldn't this cut into that? How, have people looked at how this will cut into that and the benefits or perhaps problems in the economy with that cutting into that infrastructure?
No, the short answer is no. The longer answer is it actually is not that large. What struck me is I had a slide like this where I said 70 million cars per year. And it turns out between 2008 and 2014, the rate of car production increased by 10 million per year. So you could argue that sectoral, and we didn't even see this here in the West, because most of this happened in Asia, right? So I'm arguing that on the scale of things, yes, surely it will change where resources go and where money is being invested, but it is not so large that it will ruin the economy. Put another way, if you really come down to $30 a ton of CO2, you're talking about 25 cents on the gallon, right? And my gasoline has changed by more than $1 over the last few years, up and down, and the world never came to a stop when this happened. So I think from that perspective, I haven't done the economics analysis, but I'm reasonably confident that if you work it all out, it's not all that horrible. And besides, it does create jobs.
So Klaus, I just have a question quickly. It would appear to me, following the Sherwood Rule issue, that one of the very first ways we should be capturing carbon is from fossil fuel-fired power plants, for example?
I wouldn't disagree with that. I disagree that Sherwood is right. I would simply say we don't have the luxury and time to do this sequentially. So we should go forward on all fronts. I'm not telling you just do air capture and do nothing else. If I'm radical about it, I would say put air capture in place and then force everybody else to find a cheaper solution, right? Because I think you could, there's this heated debate whether this is a moral hazard or not. And the moral hazard argument says you shouldn't do that because you delay other things. I would actually argue the other way around. I think it is much more likely that if air capture works, pick a number at $80, $90 a ton, that it is suddenly a lot easier to force that coal plant to deal with its own CO2 by saying, we don't care what you do, but if you don't do it, the CO2 comes back out of the air and it will be done on your behalf. It also goes into negotiation between countries. You could say if you import things into if we are ending up importing things from you and you are highly carbon intensive and we are working hard against it, we can settle that score via air capture. Again, you'd be surprised how much this creates an incentive to deal with this problem at the source. I see this, and some people cringe when I say it, particularly Peter Eisenberger. I see it as the method of last resort because it's going to be the most expensive way of dealing with the CO2. Because if you have a more expensive way, you're not going to use it because air capture is cheaper. So the airplanes probably have no choice. But the power plants should deal with it themselves. And yes, you should do all of these things side by side. Another argument is the coal plant, the cost of the CO2 is a big fraction of the total. So you will see a lot of resistance. The cost on gasoline is actually quite small.
Sally.
Yeah, Klaus, could you say a little bit more about the moisture swing? Like, how does it actually work? Like, how do you encapsulate your whole, gadget in something that allows you to do that moisture spring? And also, second, does it limit the climates where you can actually do that to places that can be very dry?
So here on this picture, you see an idea how it might work. We are actually right now building this sort of, think of the old computer fan fold paper. These are ultimately mattress-sized objects where the wind flows through these little filters you saw earlier. The passageways go through like this. So the wind goes through when it's exposed, and then it literally is pulled back down into the box when it's loaded, which in our case takes about 45 minutes. We are trying to accelerate that, but the material we have right now has a 45-minute loading and unloading cycle. So now that it's in the box, we make it wet. We spray water in it. In the current incarnation, we literally flood it and then drop the water back out. And then it's thoroughly wet. It will release its CO2, and inside the box you will see 3, 4, 5% CO2. If you evacuate it, which in our current design we are not planning because we are feeding it to algae, if you evacuated it, you could have now pure CO2. If you leave air as sweep gas in, you come out with 5% CO2 in that air. So that's the basic underlying cycle. If you now come back out, the system is exposed to open air again. It dries in the open air, and then it picks up CO2 again. So you actually, the water is critical as a fuel in a way, because it turns out the net result is we are concentrating CO2 500-fold, and we dilute water vapor 3-fold. And so we need 6, 7 molecules of water to match 1 molecule of CO2 to actually come thermodynamically out ahead, right? So the net result is we are a glorified swamp cooler in that we use the evaporation of water as an energy source. If you measure carefully, you can actually see as the wind blows through the system and it absorbs CO2, it actually cools. And when you release the CO2, it actually heats up because it is absorbing water, right? And so you have a reverse to the normal setup. We have in the meantime done molecular dynamics calculations and DFT calculations on it, and it's quite clear that what you see is that the hydration energies of the carbonate ion, the bicarbonate ion, and the hydroxide ion are different. And as you starve the system of water, which you do in these polymers if you make it dry, the hydration clouds shrink, and the loser, energetically speaking, in this process is carbonate. So the hydrolysis reaction of carbonate plus water goes to bicarbonate to hydroxide plus hydroxide is actually favored, and Le Chatelier's principle is not violated because it turns out there is less hydration water in the bicarbonate and hydroxide combined to compared to the carbonate. So it paid to break up one of that last waters, make a proton which ties to the carbonate, and then you have a bicarbonate and the hydroxide. That hydroxide now has an enormous affinity to CO2 and loads itself up to make a second bicarbonate. But if you now give it water again, it looks just like a bicarbonate solution. And if you have baking soda at 1 molar solution in a jar and you seal it, you have 20% CO2 in the headspace. And so that's the cycle we take advantage of. It is true, this is a specialist for dry climates. We are nearly perfectly overlaid with PV areas because dry weather and sunshine tend to correlate very strongly. The correlation breaks with altitude. We like it hot. PV cells actually like it cold. So New Mexico, we are a little more strained, and that's a good PV place. But if you look at a map where PV is and where we would be happy, I also agree fully that in the long term, we need to have more than that option. To me, there are multiple ways of doing it. And the principles we have, being passive, minimize your energy consumption, and mass produce, can be applied in the others too. Although I must admit, all the companies who are doing it right now using blowers. But if you look at it in all of their cases, the blower energy is significant in the total. And they say, well, it's not, if you look at the carbon engineering, they say, well, we go immediately to fuel, and what's the energy consumption at the CO2? It doesn't really matter because we make fuels. We started with disposal in mindset, so we have to be very, very low in energy consumption. And so therefore, we championed from the beginning a passive system. If you look at the first thing I wrote about it in a conference in 1999, I said it's passive, right? And that's what drove me, is that I figured I can't pay more than 15 meters a second because then the energy consumption ate my lunch, and so I may as well rely on the wind. And since we are humidity swing, we can't be weather independent no matter what we do, because on a rainy day we are not collecting, right? Because so we are truly like wind energy at the mercy of the weather, and our particular method really likes dry climates, and the wetter you are, the harder it gets.
Okay, with that, let's take a 15-minute coffee and physiological fluid break. And thank you very much, Klaus.